Back to another video, guys. You're on physics. This is revision. It's all about electricity, electric density, ions mobility, and finally electric current in gases. Today we're gonna be going through problem 1 dedicated to finding concentration of ions in gases using mobility. Here's an idea how drift velocity is connected with basically electric field strengths that we covered before, and just using that idea, which is pretty straightforward, we'll be looking for a concentration of charge carriers. So make sure you watch all explanation dedicated to current in different mediums, how we can arrange basically current in gases. They are not conductor under like normal conditions. However, if you apply electric field inside through the gases and also ionize somehow, that's all possible. All right, if you're ready, let's get started. So right, here is the problem. Pause the video, try to do better on. And so take into account the fact that we are going to assume that concentration of positive and negative ions are going to be the same in equilibrium state. That somehow simplify your calculations, otherwise it wouldn't be possible to find. All right, so and let's have a look at my explanation. We have the air between two identical parallel plates, and we are said that it's ionized. So what does it mean ionized? It means we have external source of energy that makes your gases and atoms that are neutral under normal conditions becomes actually positive and negative ions. So just switch to this slide where we can basically state that this is anode, positive electrodes. So actually at this plate we have positive charges, and I mean on the plate, so because it's positive it's plugged to the positive terminal. So hence the electric field inside we can consider uniform. That's the first consideration here. And obviously, due to the fact that here is the voltage along the distance d, so we can say that a electric field is going to be equal to voltage over distance. That's the first fact, and that's uniform no matter which point you take. So on top of that, because it's ionized due to UV radiation, so UV radiation, it means we have positive and negative ions. And of course, how current will be created in this case, the positive ions will move to negative electrode. In this case is cathode. Okay. And negative ions will move towards anode. All right, so we're talking about concentration. So first of all, let's remember the formula which connect the drift velocity with the electric field strengths. So that's ions mobility coefficient. It can be connected through. So, but I would like to separate for positive ions and for negative. So velocity of drift that I marked as V. So for positive ions, it's going to be mobility for positive ions times E, right? But in this case, I would use V over D. Okay, so what about negative ions? We have the same equation by using mobility for negative. So mu is going to be mobility, but in our case, we are given different mobility for positive air ions and negative air ions. So in this case, we consider that mu positive is 1.3 in terms of the unit centimeter squared over voltage times seconds, and mu negative will have 1.8 centimeter squared of voltage times seconds. All right, so now let's just go to differential Ohm's law that connects the current. So in this case, I'm not going to use the vectors. So absolute value for current. How current is created? So through the current density, it's I over the area, and also just by definition, you using microscopic definition, is going to be concentration times drift velocity. So the general formula, just remember, concentration of ions or charge carriers times E and times velocity, drift velocity here. But I would separate and I combine for positive and negative ions. And as you remember, I derived this formula already, so we can use the positive concentration and also using velocity on the drift, which is also positive. So plus, why plus? Because we also discussed this, because current will flow in both ways due to the fact current to the right is going to be from using positive ions, and current to their anode due to negative ions. So total current is going to be a summation of currents, and I also derive this. So that's why we can write through that. And also we need to multiply by the unit charge, in this case electrons. Okay, so that's the picture. But however, in equilibrium state we can assume that concentration of positive ions is going to be equal to concentration of negative ions. In this case, we consider that electrons that turn out from, let's say, neutral atom and makes this atom to be positive ion immediately reach their neutral atom. That means it becomes negative ion. So this it means that there are no any electron gases like suspended, so that electron, once it left the the neutral atom, makes it positive ion, it immediately caught by another neutral atom, which becomes negative ion. So in this case we can assume that we have in average we have concentration approximately the same for positive and negative ions. All right, so we are going to use this as the basic formula right now, and that's going to be the basis. And right now what we're going to do, we just need to express concentration. All right, so bear this formula in mind. We just go next. I'll rewrite in a bit different ways, so I just express concentration for positive and for negative. That's going to be the same, and I'll express through I over, here is going to be area, here is going to be mobilities, mu positive plus mu negative, and the total factor in this case is going to be d, distance between plates, and also we will have the unit charge and voltage. All right, so that's how we have a concentration. That's a result of the previous step. So I'll try to capture that one. So I'm not sure. Okay, just have a look, express. Maybe I'll express through there. So let me just do it this way, and I'll write the formula right now. So one more time, I'll express in concentration from here. It's going to be I over area over E, and if we write velocity through mobility, we'll get a total mobility for positive and negative, and we also have V over D, and that's going to be below. Yes, so it's going to be V and distance here. So if you just compare, we have the same. All right, so now let's just plug the numbers. So we have, I just put the number for it. So current is 3.5 times 10 to negative 3. Oh wait, sorry, wait, 10 negative 6 microamps. So microamps. Next one. So let's have a look. We have voltage, 100 volts. It's right there. D, we have 50 millimeters, but I will convert into centimeters. It's going to be 1.5 centimeters. So finally, I'm going to use concentration as in unit centimeters, -3. Okay, and what about area? So we have area 200 centimeters squared, and we have mobility that we marked before. All right, so we have all those data, and if we calculate finally concentration of positive ions, that what we are required, will be equal 529 times 10 to the power 8. So that's the final concentration, and 1 centimeters cube. Okay, so that's going to be concentration under this circumstance. Of course, if you have probably different electric field and different UV radiation, instead of UV you'll have X-rays, so probably it will influence on the current, and probably it will influence on ions mobility, because so if you change in voltage, you'll change E, right? And hence you so change in voltage, you'll change E, and as a result you change mobility as coefficient of proportionality. So that was the problem. That was solution pretty straightforward, and that's completely based on theoretical basis that I explained to you. Alright, so don't forget to check other parts of physics. You can have it on my channel. If you're new here, please subscribe, support me, and share this video if you like that. Alright, see you next time.